Okay, welcome everyone to this lecture. So today, we're gonna actually go down a road, right? So we're gonna continue, of course, talking about ANNs. And before we go down this road that consists of A, B, and C today, so remember A, B, and C, and I will explain what A, B, and C is, but it's kind of important for you to connect the dots, right? So you will find A, B, and C also in the main document. Like I re-uploaded everything and renamed it a little bit so that it becomes more clear to you how things are actually linked. So just some formalities. You can see these documents here, they are named E1 to 3. The E1 document we already talked about last lecture is the extra document. So E stands for extra. So these are documents that I create on the fly that help you understand certain things that might get lost in the main document, but without crowding the main document, this will help you. So they are always like denoted E and then 1, 2, 3, and they will have a number that relates to the main document. So we are still in O1, so artificial neural network, the first topic, and we have these documents. So E1 was bias, and so I re-uploaded it. So the E1 document we're not going to talk about today, obviously, because we talked about this last time. And now this is an additional document that is kind of an introduction to the thing that we do today, and also contains an example that you might find useful later on for the exam preparation, because sometimes I let you calculate stuff, and I hope this will help you. So I'm always trying to give you more information and give you some more input. So today our ultimate goal is to know how neural networks, artificial neural networks, ANNs are trained, right? But before we understand that, I still want to kind of stress out the concept of trained versus untrained. We talked about this last time a little bit, so I'm not going to go into every detail again. However, I want to use this metaphor again because I will use this metaphor of the quality assurance that we already talked about to show you the difference between what is possibly an untrained network, why is it useless, of course, what things are the same between trained and untrained. This is very important because people tend to get it wrong. And then, of course, we will do this with the real network, right? With the real artificial neural network. So we will go from metaphor actually to the real network, and then we will learn how it's trained and what are the differences. And then this will help us get to know how it's trained. So as this is the first step, we just explain, okay, how is this actually used? Like if this is trained, what's the difference between untrained and trained? And if this is trained, how do we use it? Which we called inference. You remember the discussion between normal time and inference time, training time and inference time we had last lecture. And then what we're going to do is something that you will actually never be able to do, right? So this is something but it helps us understand. So this is a pure method for the lecture. And I want you to get this straight. So I don't want you to think and be confused with, oh, I can also do that. I mean, you technically can do that, but it's not real good. So what we do is for one time only, we're going to do an explicit programming in that we set the parameters of a simple example. This will help us to know what the actual machine learning does when the machine learning trains it. So it will help us to better understand how the model is trained, right? But usually, obviously, we don't care about setting the parameters because this is what the machine learning algorithm, the training algorithm using gradient descent that we learned in AIBDS1 will actually do for us. So and there we actually have the answer. So I could actually end the lecture now and say, hey, we use gradient descent by everyone. And that's actually true. But there is a difficulty with gradient descent that it's not that easy with artificial neural networks because of all the layers. So there is a specialty I need to explain. And this will take most of the time. And this is probably the most complicated thing we will go through. However, and we will continue this in the next lecture, obviously, because I think we're not going to finish it today. Okay, but for now, rewind and remember this example here that I had, this metaphor. It's not really an example, it's a metaphor for a neural network. Now you remember we had this quality assurance of cell phones. So the input basically is a cell phone. So a cell phone like this, it gets in and then we have, in my case, we have two departments, right? So this is the company that does the quality assurance. They get cell phones. They must say, okay, cell phones are produced. And then this is the quality assurance. And they say if it's okay or not okay, right? So okay or not okay, that is the only decision they have to do. So ultimately you think, okay, this is a binary classification problem. This is what I hope you think, right? And so basically they get a cell phone, which is the input data. And everything I have in white here is the metaphor, so that belongs to the metaphor. And everything I have in green is mapping the metaphor to the actual ANN things, so that helps you better to understand. Hey, what does he actually mean when he talks about like how they give advice, how they give a note to the other department, right? So that you know, okay, this is I'm talking about the connection, I'm talking about the weights, and so on. Okay, but first we concentrate on the white, right? Everything in white here. Quality assurance, get a cell phone. And then I said, okay, we can imagine a neural network as having an input, which is something that people look at. In this case, it's a cell phone. And then we have several departments here, right? And so in my case, it's a very easy example. I use an easy example. This is even a more simpler example that in the main document. However, it's important that it doesn't change anything. All right, so what we have here is we have department 1 and department 2, and they receive, of course, an input in form of a cell phone. Then we said, okay, these little fellows here, they are people that work at the department, and each of these fellow has a special task, right? Looks at something, looks at the input data and decides, concentrates on one thing and reports this. For example, this one could maybe look at the display, and this one could maybe look at the button or whatever. So, in principle, they can look at everything, right? So they can look at the whole cell phone, basically. But usually, their task is then to report some findings to this person who then decides whether it's okay or not okay. So this person never gets to see the input, but has to rely on the reports of those two people. Now, then we said, okay, the neural network has other parts as well. There's a bias unit. So you can think of the bias in the input layer. So we have the input layer, which is the input the quality assurance house or this company gets. They also have like a default leaflet where they say, okay, this is like a default value when we don't get any information. And this is like the bias. This is our X0, right? This is like the bias unit, like some kind of default thingy. And this doesn't change. This is always the same. Whereas the input changes, like we don't get the same cell phone exactly ever. Like we get different cell phones and we have to check different cell phones, obviously, right? And then here in the department 1, we also have sort of a bias, which could be some sort of robot that always does the same thing. So this could be like an automated thing that gets always done, right? That doesn't need the attention of of these people here, right? So it's some kind of automation that's always the same. It's always the same. It never changes, right? And now what we can do is we can say, okay, this thing that never changes is done and is some information for this guy who decides if it's okay or not okay, right? And then this guy decides something based on the input data, based on the cell phone and the standard QA default, and decides, okay, I'll give this note. For example, display is too glossy, for example, right? And this guy says, okay, the button has some errors, right? The button doesn't press very well, right? And so this guy says, okay, so the default thingy for me is that important. So these are the weights, right? These are the weights, and they determine the importance towards this decision. And it's good that we look at this one because this one is making the final decision. So it's easy for us to actually interpret. So we have some weight given to the default. So maybe this is everything they don't check for. This can be automated. And then we have the display, and we have a weight for the display also, right? So I only drew two weights in green with the formula. We will discuss why this is called that in a second. And here is also a weight, right? So based on these weights, then this person decides, okay, is it okay or not okay? So for example, deciding and saying, hey, the display is most important if the button is like a little bit chipped. So maybe this one has a medium activation. Remember, we talked about activation. That is basically the value that the network takes. So This one is saying, hey, it's a little bit, but it's not that bad. And this one's saying, oh, the display is broken, so it has a high activation, everything goes up in red and so on. So and then we have a weight. Now, if this has a high weight here and a high activation, this will massively influence the decision, obviously, right? So it's more likely that we get not okay. So now the question is untrained versus trained. Now it's simple. The only thing we train here in this thing are the parameters, right? So if we go down here and have the actual network, so this network actually represents the house. So we have exactly the same kind of units here, right? So we have our input, right? So this is the x1 and x2, like these green things map to this example. It's the exact same example. And then we have the two workers, A1 and A2 here. And then we have A1 in the third layer. And this is our output guy. This is that one, okay? So, okay. And we have our two bias units here, right? That are always one. So this is why I wrote them in white, because they are not parameters. They are always one. Now the pink thingy here are our parameters. So the parameters are the only thing, right, that distinguish the untrained model from the trained model. This is very important. We do not like add something in the trained model. Like we do not change the departments. We do not change how many people work there. We don't change it at all, right? We also know the format of the input. Like we don't give another input variable here, right? So this is also very important. So we have the data, the input ready, and we don't change anything, right? Except the only thing that changes from untrained to trained are the pink things here, which are our parameters or weights in the neural network. And so I added the weights here. You can see that I only added them for these and not for everything, because we have the better example in not my handwriting in the actual document, so you will better see it. And this is important to understand. So I'll repeat again. The only thing that changes is the parameters. And now if we look at this from the example, right? What does untrained mean? Untrained mean we just put some people that are absolutely not qualified. So you can think of they have kind of an empty brain, kind of the kid that we want to show what a sports car is like before the mother shows the kid, right? So we have untrained means we have workers in department 1 that don't know what to do with the cell phone. Like they have no idea. They get the input, like they get the X1 and X2, like they get the cell phone, but they have no idea what to do, right? So they basically randomly report something back to this guy here, right? And the workers, or in this case, the worker in department 2 doesn't know what to do with these comments that these workers give him, right? So, and the problem is obviously our output then makes absolutely no sense. Like we also, this one knows it has to give an output that is okay or not okay, but the output is absolutely random. So it's bad. So the output is either okay or not okay. So it doesn't say anything else. This is very important because this is also the structure. However, it doesn't make sense and it's probably not correct, right? For most of the time. So, and trained means they actually know what they do. They know what to look at. This one knows how important these inputs are, and the output's actually meaningful. And I wrote hopefully correct. So, of course, a trained model is not perfect. Like you remember in AIVDS1, there was not, like we discussed this, there's almost never like 100% accuracy. However, it should be meaningful, so it makes sense, so it's not random. And this is the crucial thing. This is the most crucial thing. Now, let's go and see what this means for our actual ANN. So I've done the same thing with our ANN now. So basically what this means, we start out with an untrained model. Like before we train the model, we have the architecture. So this is very important. The architecture we have, so everything in white here we have, right? However, the model is untrained. That means all weights are random. You can also say, if you like it better, you can also say the weights are all zero. This is because we initialize the weight before the training process. If you want, you can say that the weights are all zero. Like the weights, they are random or zero. So usually we initialize them random, but in the real procedure, if you like, you can say they are all zero. Like there is no combination, no weight, whatever, right? So we know the weights exist, but they are all zero, right? And this means that the activations A here are totally random because they are influenced by the input. Like we can give them some cell phones, so they of course depend also on the input data. However, the weights will make them totally random as well if the weights are random. And hence they are disconnected from our actual output that we want to achieve. Now we will get a value somehow here, but the value will not really reflect the input, right? Because the connection from the input to the output is governed by these weights. And if the weights are random or zero, then we get zero. In a zero case, we would get just always zero, right? Okay, so I hope this is clear now. And now we are going from A to B to C, right? From A to B to C. Now, as I said, A is actually how we use the network. So A is actually from left to right, how we use the network, right? So this is actually A. So A is we have some input. We put in some input, x1, x2, like some numbers, like 2 and 1.5, for example. So some numbers. And then we go from left to right, and then we get an output of whatever, right? Maybe like this. And how we get from here to there is A, right? So this is what we speak first of. And this is called having an input and then a network. It doesn't really matter if it's trained or not, right? Because we know that the architecture doesn't change. Now, if we put this into production, we better use a trained network, right? But these weights could also be zero. In that case, this would be zero, right? And this process going from here to here, I teased it last time a little bit. It's called forward propagation. And it's pretty easy to know because we go forward from left to right. We just go forward. It's called forward propagation. And this is a very, very important concept because we also have to do it during the learning process, right? Because we have to basically test how good the network is. And therefore, we have to calculate the output, right? So basically, this is forward propagation, right? What I have here is a small example. I won't go through the example in detail. You can read the example. It's really easy. The important is from left to right. And so I have a network, exactly this network. So this is an example, of course, for this network. And I've given you some weights here, and I've given you some inputs. We have 1 and 2 as inputs. And then you just calculate from left to right until we get an output. And I actually wrote it here not in my handwriting. So you actually have the numbers here. And then we get a final output here for this network, right? This is just an example, right? You can study it if you want. If you don't understand it, we will do some of these calculations in exam preparation. But just so you know, this is something that I could potentially ask in the exam. So A, forward propagation, go from left to right. I can't, however, ask you to train a neural network on paper. This is I could, but it's hard. So it's not really a thing to do. But I could easily ask you to do a forward propagation, right? So that we get an output that you know how this neural network works. And it's also important because you get to know what these values look like. So you can imagine it. For example, we get these outputs here. Now those are the outputs for our hidden layer. So you can basically see how they impact the final decision here, like with the minus weights and the plus weights, and you get an idea, right? You get a basic idea. And I did on purpose that they are both 4, but they are differently weighted, so they are differently going into the decision. Just like it would be in our original example where we say, okay, maybe the display that this guy has more influence on. However, but it depends on the activation. Now remember that the activation could be low if the input is low, right? So the activation always has 2 influences, right? The X and the weight. Now, if both are high, then we have a high activation. But for example, let's say this is important. So the display, so this is a high weight, but X1 is small, right? Because the display is fine. So that means if the display is fine, X1 is really small. Then if it has a high weight, but multiplied by a very small value, then we have a low activation, right? It's very important to know that, of course, it depends on the data, but it also depends on the weight. So the weight is set once the model is trained, and of course the input changes. Like which makes sense. So if you put in a broken cell phone, we want not okay, right? We want not okay. But if we put in like a cell phone that is totally all right, we want okay, which makes absolute sense, right? And the weights, of course, the same, because when the network is trained, the weights are of course the same. Like we can deliver it. Remember when I say we go into a shop and can buy a neural network, we actually buy the weights and the architecture, right? And then we just put in data and look what's going on, right? And so this is sometimes they also call what's happening inside here the black box, right? So whatever it is, we just put something in, we get something out, and we can use the network, and it might work well, it might work not so well, and that's it, right? So, and this is our introduction for today, basically, right? So what we're gonna do is we're gonna change to our main thing here in a second or right now. And now what we're gonna do is now we have ABC. So this is the logic for the lecture, right? So this is for people that do not or they revisit the actual lecture. So you're gonna read E2 for intro. We did that, right? So we just read it, we went over it, it's fine. Okay. You can also practice. I have also an E2 example. This is the calculation example. So A is how we use ANN. So this is forward propagation, right? We will talk a little bit about how we denote. We will use this to talk about the notation a little bit. And then B is this thing where I said this is kind of what we not usually do. We train an ANN by explicit programming. So we choose the weights. Remember, we never do this, but this time we're going to do it to understand what the actual training process does in the end. Like how could it work? It gives us an understanding if we do it ourselves, right? Okay. And C, of course, is then how do we actually train? Like what is the machine learning way of training the weights, which we actually want to achieve? This is our goal, and we will reach this goal today, and we will continue to discuss it in the next lecture. All right. Now, let's see. Let's talk about it. Okay, forward propagation, very easy. So last time, of course, we talked about how neural networks are built, about the bias unit, blah, blah, blah. We did all this. Don't have to tell you. And now we're going to focus a little bit on the notation first, right? This is probably going to zoom in a little bit so that everybody sees it. So here we have another example, right? You can use, it doesn't matter if you use this example or the example in E2. It doesn't matter. So you can see this network here. And the only thing I want to explain is this all I did here is explain the formula, how we go from left to right, like how we go from the input to the output. And these are just the formula. This is just a formal expression of that, nothing more, right? It helps us to generalize. It helps us to generalize a little bit the whole thing. Now, okay, so we have a couple of thingies here and a couple of indexes, a couple of powers here. And so let's denote first this A thing, because this is what we don't know. Now we have the input layer. This is always denoted. The first variable is x1. Remember, we have an x0 here, right? Don't forget the x0, because usually when we put this architecture, when we draw this architecture, we assume a bias unit. So we don't draw the actual bias unit, but I want you to remember that it's there. The same is here. We have A0, right? A0, 2. We also have this here. So please remember this, right? You can see here it's drawn, right? Here we have it, right? So but usually it's not given when we draw the architecture. Very important, remember it. Also in the exam, I tend to not give it to you, but I will say we assume a bias unit, okay? I will give you the idea, but you have to make sure, okay, you use it in the calculation, right? Let me just get a little bit smaller here so that I don't, because we have a high zoom. Okay, so we go from left to right. So the first thing we calculate, so what I usually would suggest you do is you start here in the first hidden layer and go from the top to the bottom, right? An advantage of not drawing the bias here is also that sometimes students calculate the bias, but that's wrong because the bias is always 1, right? The bias is always 1, right? This isn't calculated. There is no connection here. Forget about this, right? This is completely wrong. And I think I told you last time. So, and go from left to right, top to bottom. So we're going to start in this layer. So first of all, each layer is numbered, right? So this might be important. So the first thing, I would number each layer. We start the input layer as 1, this is 2, and this is 3. This will help you out, right? Because we have the activation here, the activation of unit I in layer J. So unit I is the number from top to bottom, and J is from left to right. It's pretty easy. Left to right, top to bottom, right? So A, I, J. So unit I, so the first one in the second layer. So this is the first one in the second layer. So the first one in the second layer, so this is the first unit, right, from top to bottom, and it's in the second layer, right? So that means that all units in the same layer, right, they all have the 2, right? So all units from top to bottom need to have the same power because they're in the same layer. Now, if I ever see something like this from you, right? So this is a neuron, and this is wrong. This can never happen, right? It doesn't make sense, right? This needs to be 2 also, right? So, and that's basically it. And this is how we denote them, right? So because we need a system, because usually we have like a lot of neurons and then not only like 2 or 3. And now the most important thing, so we have a matrix of weights. Now we have a matrix of weights controlling function mapping, and this is important. The J, the power, the J is the layer where it starts. We denote the layer where it starts to the layer where it goes, because weights always go from one layer to another, right? You can see this here. Goes from layer 1 to layer 2, right? Goes from layer 1 to layer 2. Goes from layer 2 to layer 3. Okay? So, and we always use the original, the layer where it's originated, right? And yeah, this is the writing. And now for some examples. So I guess this is okay, right? So this is pretty easy to understand. But for the weights, let's look at this weight right here. This weight right here. This is our example weight right now, right? And I'm gonna explain the notation of that weight. Okay, so obviously this is an element of the matrix, right? This is an element of this matrix, so we always write this. This is the large theta. You remember our parameters were always denoted with theta. And then we have 3 things. Now, it gets a little complicated. So the first thing you always start with is the easiest, is the power, right? So, and this is easy. This is from which layer to what layer? And we take the from layer. So this is from the first layer to the second, right? So check, this is from the first layer to the second layer, right? And it says matrix of weights controlling function, blah, 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 from layer J to layer J plus 1. So, and here we have J, that means, okay, this is from layer 1 to layer 2. It would even be cool if this was like one arrow 2. I would love that, but yeah, this is not how mathematicians think. So this is from layer 1 to layer 2. And now we have 2 more, because from which unit in layer 1 to which unit in layer 2, right? So we have many units in layer 1 and we have many units in layer 2. And the only thing I need to denote is the number of this unit and the number of this unit, right? So, and now this is where it gets a little bit confusing maybe. So it's always not from where, but to where. This is the only confusing thing. And this you have to remember. It's always to where, right? It's always to where. So here, in this example, we don't care about the input. We care about where does it go? It goes to 1. It goes to the first element, the first unit of the first hidden layer, right? So, which is the second layer. Like the first hidden layer is the second layer, okay? But we have fixed this already with this, so we don't care. So the first number is always to where. First unit and from where. First unit, 1, 1, right? Having a check. Now let's check this out and see how we would do with this connection from here to here. Now let's check this connection, okay? let's do this as another example, okay? Oh, sorry. Let's do this one as another example. So this is here, and this is another example. Again, we start with theta. Okay, it's the same because we have from first to second, right? So this is one, it's also, and now we start by to where, and it's two, it's the second element, right? Where does the arrow go? It goes in the second one, right? And it comes from the third one, right? So to where from. So this is to, and this is from, right? And this is from layer. From layer, from neuron to neuron. Okay, I hope this helps. Let's check if we understand this. So, and let's formally write down the calculation. So, the input is not calculated, it's given, obviously. We don't need to calculate x1, x2, x3, x0 is 1, of course, we know that. So the first thing we need to calculate is the first neuron in the second layer, so the first neuron in the first hidden layer. And so we always start inside this, right? And what I suggest, please, like apply the activation function G afterwards. Do it in 2 steps. This is also what I wrote in the example in the E2 document. So I recommend doing basically this. I recommend first like calculating a value like this, where I just use the inner workings, right? Like this here would be set 1, 2, and then just applying the G function, our function, to set 1, 2, right? So just have the linear combination and then use this value. And also in the exam, make 2 steps, because if the end result is wrong, you get 0 points. But if you have like the intermediate result, right, you get some points, right? Just a quick advice. But you might know this from RBDS1. So this is my suggestion. And you also did this in a logistic regression. So this is basically the same. It's not really different. Like you remember this. This was actually a task in the ARBDS1 exam. So we didn't have to do it that often, but just once. So here we have to do it quite often. In a logistic regression, we just do this once. Like this would be our output. But here, so basically, when I said at the beginning, we just do many logistic regressions and put them together somehow, I was obviously not lying because it's always the same. So, and here, I will explain this line real quick, and then you can like check if you understand it with all these other lines, right? And maybe I'll explain this line also because it's like a little bit different, but not really. Okay, so we start at the left-hand side. So we start with the first thing that is the weight that is multiplied to the constant, so to the bias term. Remember, the bias term has a weight. So we're actually talking about this connection right here. That is not shown. This connection is not shown, right? So this connection is not shown in the picture. So this is actually the weight for the bias term multiplied by x0. So I could also write, since this is 1 here, I could also write 1, right? Sometimes the bias term is not 0, right? In rare cases, the bias term is not 0, so we keep it general here, but for our purpose, we assume this is 1, okay? And this is the weight for the bias term. And you can see we have, let's check if we understood it correctly. We have 1 here because it's from layer 1 to layer 2. And then the first thing, to where? Yes, to the first unit. And from where? From the 0, from the bias term. And this is easy. You can always see if you're correct because of the bias term, right? Because there is no, it can never be, never ever, that there is a 0 here. Why not? Why can it never be that the 0 is the first number? So you will never see a weight like this, for example. While you type in the chat, because I'm sure you know. Why can't there be something like this? It's really important that you know that. I told you in the last lecture, and I also told you just maybe two minutes ago, right? Let me see. Yeah. Oh, I love Jonathan. Yeah, Jonathan, this is right. There is no error to the bias term. I remember how I vividly expressed it. Yeah, because there's no connection bias code. Perfect. Yeah. So there is no input. These are always one. They are not calculated, right? So it makes no sense. So this here can never be. Very important. Wrong. Okay? Cool. Um, but you can check, right? This is easy to check if you got the notation right. If you ever write something like this, you know this is just plain wrong. So sorry, sometimes I have to see where my cursor is. Okay, and then we go on, and then so we have this is that connection, right? This is this connection, right? And then we just have all the connections from x1 to this, from x2 to this, right? And obviously from x3 to this. So this one here, this is the first connection. So let's call this W0. So this is basically W0 here. This is W1, this is W2, and this is W3, right? So just to translate my old W notation for once and for all, because we will use the other notation, but just so you know, and this is W3 here, okay? So, and now you see why we can't use this, because then we have like W1,800,000, whatever. So, and this is why we use this. Okay, so this rate, of course, check it again. Again, where to? 1 from 1, where to? 1. So they are all in one line. Basically, there are some rules you can imagine, like this number right here is odd. Oh, cool. It did automatically stuff. This number is also, now it doesn't. Need to be really cool here. This number is also always the first number here, because this is where to. All the connections go into A1 of the second layer, right? So these numbers all in one line all need to be 1. There is no exception. They all go there, right? So that's basically it. And now it's really easy for you to understand this, right? They all go into the layer, so into this neuron, so it has to be. Okay. And so we calculate this number right here. So this has then this is actually a number, right? So we calculate this, the inner thing, the sum, right? As a first thing. And then we calculate this so the inner sum. So this here as a first thing, right? And then we apply our function. My God, I have to make it bigger. I'm sorry. My monitor is too big. I just cannot see it. I'm sorry. I otherwise cannot see the cursor. And then we just, oh my God, then we do this, apply the function, and that's it then, right? So, and then we get a value. And this value right here is the activation. So remember, high activation means, okay, there is something maybe important there. And low activation means it does not have a high impact on the end result, right? But we don't know because there are multiple layers ahead. So the problem is if this has a high activation here, this is actually because this is directly connected to the output. I can already tell you that this will have a high influence, right? Now, if we have more layers than that, I'm not so sure because I'm not sure how this high activation translates all the way to the output. If we have like, let's say 4, 5, or 6 layers, right? It could be diminished in the course of this whole network. So we are not sure basically, right? So we are not sure basically what the input is. So, okay, same goes here, like A2 to A3, A3 to, and now we come to this one, right? Come to this one, and we're going to look at these 3 thingies here, right? At these 3 connections. So we're going to start. So basically, in our case, A13 is the same as our output. This is already the output of our hypothesis. So remember when I said, okay, this is basically a normal logistic regression at the end. Like this right here. This right here is a normal logistic regression right here. Okay? And we just generate features in P4. So this is basically it. So this is then our normal logistic regression, it's calculated exactly the same way, right? But instead of x, you can see here, that is no x, but these are the values of the previous layer, which is the first hidden layer. Now we start here with A02, which is 1. This is 1, right? This is a constant. This is 1, right? This is the constant. This is the thing right here. This one right here. This is the constant, okay? This is 1. This is the weight for the constant. Then we have the weight for our first neuron of the first hidden layer, of the second layer. And here we have the weight regarding our second neuron, right? A real neuron, right? Our second neuron. This one, the green one, sorry. Yeah, and then the third neuron, of course, this one. That's the influence. So basically here, these weights right here, these I could actually interpret, right? So these weights determine the direct influence, sorry, this one also, influence on our output. This is our output. This is the number that says if I have a classification and if this is larger than 0.5, I'm going to say, hey, we're going to take this class. Like remember cancer, benign, not benign. If this output, if I use a neural network for that and this output is 0.89, I would say, okay, this is a malignant tumor, maybe. Okay, so, but do you see the problem? Now I say, okay, this is interpretable and I underlined these weights because these weights give me direct influence. But when I say interpretable, what's the problem now? What's the problem? And this is a beautiful thing because you can directly see from the actual notation that we use, right? Just from the notation that we use. Sorry, from the notation that we use, how the whole problem of explainability comes upon us from this equation here. What's the problem? Now we have the weights. The weights, okay, we have the weights. There are some numbers, okay, blah, blah, blah. And what's the problem in this equation when it comes to interpretability? Now think about, we want to explain how this number came upon. This is our output. This might be the output that decides whether a tumor is benign or malignant. Okay, so this is very important now. And I said, okay, we have the weight, so we can directly measure. So this weight tells us the influence of the constant. Okay, we know the constant is 1. This might not be very interesting to us because we can't really do anything. And this weight describes the influence of that variable. And this weight describes the influence of that variable, that weight of that variable, right? So we have the weights. So if this is a large weight, right, we know that this has a high influence, right? If this is a small weight here, for example, we know that, oh, this is not a high influence. And if this is also small weight, so we know that this one here basically influences them all. So, but what's the problem here? What is the problem? Now, why have I only talked about the weights? What influences the output? What does influence the output? Two things. There are two people that need to tango here, right? What's the other thing that influences it? Just look at the product. You're way too deep now. Just look at the product. I'm going to write it down. Just write a simple product. What influences this result? Just in that basic thing. What influences that result? It's a very simple question. What influences that result? A and B. Totally correct. Okay. What influences that result? What influences that result? That number here. It's the weight. And what else? G and the rest of the thing brackets. Yeah, G is always the same. The weight and the output from the neuron. Yes, weight and bias. Yeah, this is not a bias. What I'm talking about is like the bias, of course, is always 1, so we don't care about that. right? So sometimes the weight of the bias is also called the bias, or this is sometimes called the bias. But for us, it's that, right? So you're correct. The value of the neuron, the activation, we call this the activation. Remember? The weight and the activation. It's weight and activation, right? The weight, we know. The weight just says, this is basically, as the name says, it weights, but also the activation. And now that you know what influences the output, what's the problem? What's the interpretability problem? Why am I not happy? I mean, the weight is not the problem, obviously. So what is the problem? And why is it a problem? You need to think, critically think. If you don't know, look at this. What does interpret mean? Now, let's assume the result is the blood pressure. So, and there is a weight and there is a variable that influences the blood pressure, right? The weight says how much this variable influences the blood pressure. What's the problem here? Now here I can say, for example, I can say uh, with each time when A grows by one, right, by 1 unit, or then I have this weight connected to it. Yeah. So this weight says, okay, if A gets like +1, right, if this whatever this variable is, then the blood pressure rises on that amount multiplied by the weight. So 1 times the weight. Okay, so I have a direct connection. What's the problem here? You really need to like think about that. It's very important because this is the root of a lot of evil things, or a lot of disadvantages in neural networks that has a lot of research attached to it in the last 10 years. This is why we need. This is the whole reason why we need XAI. I'm gonna give you 1 more minute. You need to think about. Like you can type in anything in the chat, but it's really important that you get to this on your own. Like think about it. Analytical thinking here. Okay, I'm give you one more. One more. So A is age in this equation. So I have a factor age multiplied by a weight equals blood pressure. So the weight is 1.5 times age is the blood pressure. Now that means that if I grow older, my blood pressure rises a little bit, 1.5 points. Activation function is not impacting end result as high as we like. That's not the problem. Like this could be a problem, but it's a technical. We don't know if it's the age or weight which has an impact on the output. Ah, more general. Okay, so I ask you directly, what is A12? What is this? This is just some bullshit value between 0 and 1 because it's sigmoid activation, right? So you can see how we calculated it right here. It's A12 like right here. But it's some random value. It's not the input anymore. We cannot interpret it. Anything we do, anything we do here we can interpret it because we have age. We know what age is. We can determine the age. You know what age is, right? However, I don't know what this is. This is just a value that is between 0 and 1. I know it was generated by a neural network, that I know, but I cannot interpret it. It's just what does it mean if this value is 0.5, right? So I'm gonna say with each increase of A12 by 1, right? Which is stupid because it actually, well, the activation is between 0 and 1, but with each increase of 0.1, for example, my output probability of a cancer grows by that amount. Now I could say that because it's actually in here. Now this is a valid sentence because it's actually in here, right? However, I have no idea what this is. This is just a random value based on other values, based on the input. And it gets worse if I have even more hidden layers, right? So if I have like 7 hidden layers, then the last layer, I have no idea how this is formed. And this is the interpretability problem. This is where it all comes from. This equation right here. The equation for my output does not depend directly on the input, right? It depends on transformation of nonlinear transformations of the input, right? And this is a problem because I cannot directly interpret it because it's not as easy as H and blood pressure. And I want you to remember this, right? I want you to remember this, that this is why we need XAI. And it gets worse. Like for this, you could probably say, yeah, but I can track it back a little bit and calculate partial weights. And you would be right. This is the technique, right? You could maybe come up with a way on doing this, but you have to come up with a way. It's not directly apparent. And this tracking will also have some disadvantages, right? So it will have some major disadvantages. Okay. All right. So forward propagation done. Now, pretty cool if you want to. This matrix that we have, like this matrix right here, it has dimensions, and it has dimensions of it's dependent on the units in layer J and the units in layer J plus 1, because this goes from layer J to layer J plus 1, and we start with to where and from. We have exactly this. So network has Sj units in layer J and Sj plus 1 units in layer J. We have Sj plus 1, right? The dimension is Sj plus 1. So the number of neurons, and this is the number of neurons without bias. It's very important. When we talk about neurons, the bias is not a neuron, right? The bias is assumed. So this is, oh my God. So this is without bias. Because you see, in the next thing here, this is the bias. Because obviously nothing connects to the bias. I love that someone that was really, yeah, nothing. So nothing goes in the bias, right? So there is no weight here. So this connection is missing, right? So that we have the numbers here, right? And this number. So here we can see how many weights do we have, right? So we have Sj plus 1, right? So how many neurons do I have in this layer? We have 3 neurons. 1, 2, 3 neurons without bias, right? So we have 3. So for this example, the matrix in this example is 3. And then we count Sj. So how many neurons, not biased, do I have in this layer? It's 1, 2, 3. And now the bias unit counts because there are weights from the bias unit there, right? But there's no weight into the bias unit, right? This is very important. Since this weight is not here, we lose this plus 1 here, right? So it's 3 times 4, the matrix in this case. Okay, just it's also a nice exam question, right? Nice exam question. Okay, now forward propagation, vectorized implementation. You can read this, right? So if you want to implement it, you usually want to implement it as a vectorizer using multiplications, vector multiplication. So you just usually don't have like x1 or blah, 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 but you just have like a vector that you multiply, right? And then usually you also call, instead of using x, you call it a1 so that everything is the same. So we have, this is basically not x1, but this is a11. And so you basically, this is easier because you can then also loop through it. You can easier multiply through it. And it's easier to determine because you can then use the same notation, right? And yeah, you start with z, right? The inner workings, then you apply the function like you do it in 2 steps. Also, you would always do it in 2 steps here. And then you add the bias unit, right? Blah, 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 as a vector also. And then what you do here is you then calculate it as a vector. So this is like the matrix, like you have this matrix here and you multiply it by your vector and that's it. That's basically it. And then you get the output. So this is just a vectorized thing because usually we will always use like vectors and matrices. And if you've asked yourself, how can we do that? This is your answer. Like this is just a formal extension. If you're familiar with vector and how we write vectors and matrices, this should be nothing to you, right? It's just basically the vectorized writing of this one, right? It's easy. So you can see this right here. Okay, cool. So if you want, you can always also write it in vector form. Like to me, it doesn't matter, right? So, but just when you implement it, obviously, a little bit of background why we not like put everything in a single number when we program it, because we want to use frameworks, efficient computing frameworks, like where we have matrices and tensors that can multiply pretty fast, like 2 matrices together, for example, to do this, right? Because we have to do this forward propagation all the time. This forward propagation is really important because in our gradient descent, we always have to calculate a value, compare it, and then we have to learn what went wrong. And this brings me almost to C almost, but we have to do this quite often. So just to say, this is very important. And so this is where we have efficient frameworks like, for example, TensorFlow, right? TensorFlow is basically a computing framework that at its core, like it has a lot of nice functions as grown and so on, or PyTorch or whatever you want to see, but it helps make the core operations to train deep neural networks just faster, computationally faster, right? So also, if you ask yourself, if you implement things, try to avoid for loops, right? Like you could also do this in a for loop, like for blah, 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 multiply this with that and this with that. Just try always to use like vector, like transpose, like try to multiply it to get your results, right? This is better, right? It's more efficient, computationally more efficient. And there are a lot of frameworks that support this. There are not really a lot you can do to speed up for loops because it's one after the other. It's always sequential, right? So it's pretty hard to do. All right. So going on, blah, blah. This also we had, like, this is where I said, okay, neural network learning its own features. This is just what I said. Also, I told you on the Blackboard where I see, okay, this is basically a logistic regression here, right? And this is feature generation. So we have 2 steps. Step 1 is basically feature generation. And step 2 is the actual classification. But I already told you as at the beginning as a motivation. And now we are in B. What we're now gonna do is we're gonna act as if we are the trainers of a neural network, right? So we are now the trainer. So what we actually do is something we try to avoid to do, or where I told you basically that it's bad, or I mean, we do it sometimes, but never with neural networks, is that we are now the trainer of a neural network. So this is somewhere in between untrained and trained, but we are the trainers now, right? So usually our parameters would be given by machine learning, right? So that means by using gradient descent and all the stuff we learned. And so now what I want to do is I want to go through a very simple example. And the example is, again, we have x1 and x2. And we have basically 4 cases here, right? We have 4 cases. So, and it's basically that case right here. So it's a non-linearly separable data set where we have X's and where we have like O's, X's and O's, and you cannot linearly separate. You can try to build something, but you will not make it, right? So we decide to do something more complex, and we decide to boil that down to an even simpler case where we only have these four combinations. Like we cannot have, so that means that x1 can only take on values 0 and 1, and x2 can only take values 0 and 1. So we have only binary variables, ladies and gentlemen. So it's really, really easy. So it reflects that case, but we make it even more simpler. So they are binary and can only take on values 0 or 1, as you can see. And this means we have 4 combinations. So there's a combination where both are 1, right? This means we have both are 1, like this is here. We have x1, x2 are both 1, right? So they are both 1. X2 is 1, x1 is 1. So here we have the value where x1 is 1 and x2 is 0 and so on. So, and now what we actually want to do is we want to learn a classifier for this, right? We want to use a classifier for this, and this is combined to logic. Now, if you're into computer science, right, I try to avoid it a little bit because I'm not good at logic. I actually failed my logic class. I then later did not. I had to do it again. So I'm gonna tell you. But these things are quite easy to understand, right? So, and actually this right here resembles, since 0 is false and 1 is true, right? So you can act like it. This actually resembles the x1, XNOR, x2, right? x1, XNOR, x2. Like this is like an operator, a logical operator that we can build with a neural network, right? So, and what we're gonna do is, as in a neural network, we're gonna have our neurons give different tasks. So each neuron has a different task now. Remember, like in quality assurance. So the first neuron we're gonna look at is the OR neuron, right? So this is nothing but the OR neuron. This is our guy, and this is our OR guy, right? So let's say it has a little flag that says OR. That's the ugliest flag I've ever seen. I'm sorry. This is the OR, maybe a head. I really should never draw. Okay, so example OR function. Okay. Now, if you don't know what the OR function is, it's pretty easy. It says basically if one of 2 are true, then the whole thing is true, right? And remember, 0 is false in this case, and 1 is true, right? So this is the connection to logic here, right? So let's see. We ignore for a moment, we ignore this. So ignore this for a moment. So basically, the OR function says if one of them is true, then the whole thing is true, right? So basically, the only thing where the OR function is not giving out true is, so the OR function can also say 0 or 1, right? True or not true, is when both are not true, like when both are 0. So, and now what we do is explicit programming. We try to come up with these weights. This is our task now. We come up with these weights, right? So that the output always works. Now, why can we do this? Because our input is binary. So this is either 1 or 0, and this is either 1 or 0, and this is always 1. And this will also show you the importance of a bias unit as some sort of starting point, right? So you can see here, we always start at -10, right? So we start at -10, and then basically remember how G works, right? I'm just gonna draw it. G works like this. So we have this function, and basically we want this function. So this is 1. This is where it takes on 1, and this is 0, right? So, and the OR function, now 1 means true, and 0 means false, right? So we want the network to spit out 1 in certain things, right? So, and this is our G function, and we know that if the input of our G function, Z, right? If Z is really large, so basically if Z is really large, then this means this is actually great, right? So if Z is large, so positive and large, right? The more larger it is, the larger it is, then the higher our G is, and the opposite is true for negative values, right? So this is negative, this is positive. So so basically we want this to be 1, the output, or close to 0. So we take, first of all, we take large numbers, not like 0 point something, but we take -10. Okay, so if we have -10, so if we have G of -10, we can be sure, so we start at the basic. We don't care about these two, we start at the basic. So G of -10 means that these two, like these two are 0, right? So if these two are 0, then actually the output of OR is also 0. Like here in this case, this is the first case. So our output is 0. So G of -10 basically is 0, right? It's large, it's negative, it's 0. And this happens when, so this is how we can actually interpret the bias. When our other inputs are 0, what happens, right? It doesn't necessarily mean that the result is then 0, right? So if we don't have a bias, right, and we have these two weights only, then the result would be 0, which was not appropriate here. And this shows you the role of the bias also. It's kind of an offset, like a thing we start from, right? So if our other parameters are 0, okay, so we can see, not the parameters, sorry, the inputs. I'm very sorry, not the parameters, the inputs. Sorry, crucial mistake. The inputs are 0. Okay. So, okay, so this case is, so we start with -10. And now the question is, every other combination, the function has to spit out 1. Because it's OR, right? So there are 3 more cases, and you can see the cases here. Like we have the case where either one of them is 1. These are these 2 cases where either x1 or x2 is 1. And that if it's OR means just one of them has to be true. This is what OR implies. Like, for example, if I give you the choice to say you can study this, you can take this class or this class, right? To pass your exam or to get your grade, you can use one or the other. Most of you will not like take both classes, right? For those of you who want to take both classes, this of course is also fine. So if both are true, then it's also true. So what we need to make sure now is that for these combinations, everything is larger than 0. So it's +10. So we have to make sure that it's +10 or even more, right? So that is positive. And so if we use -10 here, so it's pretty easy. You can see this. We use -10 and we just assign weights that offset the -10. So -10 plus 20 is +10. So if this is 1, this is G of +10, right? You can see here, this is G of +10, right? Here, this is G of +10, right? And here, what's that? What's that? This is G of, what's that? So this is G of +10 and this is G of, what's the value here? Calculate it here. If both are 1, what's the value I put into here? I mean, it's definitely 1, we know that, right? But what's the value here? Just a little check if you're awake. You can use this. Like you have the equation right here. And you have the x1 and x2 values. Just have to calculate it. 30. Yeah, that's right. So, and this gives us exactly what we need. Now we trained it by explicit programming, by thinking, and usually we don't want to think, or it's not that easy. And of course, the real problem is that these values are never binary or rarely binary, right? At least not binary exclusive. We don't have exclusive binary values. Okay, so we did the OR guy. Thank you so much, OR guy. Now we have the negation, which is the NOT guy. So again, NOT also has a head. This is the NOT guy. Okay, so not is pretty easy. Not just says, okay, whatever x is, our output is the opposite. And it's pretty easy. So we don't even have two, we don't even compare two, but it only applies to one single input. So we just need this input and it's pretty easy. So basically, if x is not true, so if x is 0, then we need a positive value, right? And if x is true, we need a negative value. So it's pretty easy, right? So what we're going to do is we start out with the basic value of 10 that says if x1 is 0, right? Then we have g of 10, which is positive. Now, if it's not true, it's true because g of 10 is 1. And on the other hand, if this is 1, so if it's true, we want it to be a negative value. So we offset the plus 10 with minus 20, get minus 10 and it's 0. So that when it's 0, it's 1, and when it's 1, it's 0. Pretty easy, I guess, right? So, and now we need to put it together, right? So, okay. What we now have is we can also, so we have the OR function, and so, and then we can also have like the end function, like you can derive the end function is pretty easy. So that means that both of them have to be the same value, right? So, and it's pretty easy here. So we have it here in the end. I think, like, let me just see. I think they are, let me see if they are just a little bit. Oh my God. Sorry. Sorry, my OneNote crashed. Very sorry about that. Share it again. Uh, Very sorry about that. Okay. Yeah, I think this is kind of, let me see if it crashes again. Okay. Huh? Okay, I'm gonna fix this. Like there's actually some explanation of the end here, right? But it doesn't matter because we have it in the final thing, and you can do the end here. You can actually do it by yourself, right? So this is basically the homework, right? So do the end by yourself, right? You see it in the final table. End means basically, so the end table is with x1, x2, and the end. So this is how it should be, right? So if x1 both 0, 1, 0, 1, oh, sorry, 0, 1, 1, 1. So and is only true if both are true, right? So and is basically 0, 0, 0, 1. So they both have to be true. So the offset needs to just be larger, right? The offset needs to be larger. So it's only offset by these two. So we could actually, what would be an idea here? Does someone have an idea for the weights here? Like you can write the weights like this, right? Like the weights here are minus 10, 20, 20. Okay. Now what would be good weights here? So that we get like G of 10 again, for example, right? What would be good weights? So basically, we can choose a higher offset here, right? So we can choose a higher that is not offset by 1, right? So if we choose like minus 30 and have 20, right? So if we choose like, for example, what would you say to this? Would this work for end? You want to check? Let's check. G of, okay, we have x1, x2. Let's check if this would work. Okay, let's do it together. So we have again 0, 0, 1, 0, 0, 1, 1, 1. Okay, now let's do this. Like, let's try this. Okay, so let's try these weights for end, right? So, okay, so this is basically G of minus 30. which is obviously result is obviously 0, right? So this is way too negative. Okay, the next one, we have g of minus 30 plus 20. So this is g of minus 10, which is also 0. So here the same thing, g of minus 30 plus 20, which is also kind of 0. And here we have g of minus 30 plus 20 plus 20, which is g of 10, which is 1. So this would work, right? So this could be the end, right? Now I've done your homework for you. Okay. Sorry. I was curious myself. Okay. And now we can also like put it together like and not. And now we put it together. Now the XNOR framework is pretty easy. So what we have is we have this one. We have the input, right? And here we have an AND. So we have an AND, and then we have an not x1 and not x2. And this we combine to our final table, right? So, and this is pretty cool. So what we have is, again, we have our inputs 0, 0, or 1, 1, 0, 1, 1. And we want exactly this, right? We want actually, if both are the same value, right, then we want it to be 1 actually. But we cannot do this with the usual logic. So we need to combine it. So, and let's have a look at this. So first, we have this neuron right here. The A1 neuron in red is our end neuron, right? And you see our end neuron. These are the weights. Oh, see, we actually have the weights. I could have just looked at it, right? So we have minus 30, 20, 20, the thing we just put together here. You remember the homework. Put it together here, right? And so we have the end here, put it together, minus 30, 20, 20, and we get the end, right? So this neuron is responsible for the end. And this neuron right here is not x1 and not x2, right? So basically we have here the weights 10, minus 20, minus 20, right? So it's not x1, not x2. And we have this right here. We have the weights 10. So this gets offset, right? By only if they are both 0, and we get x1 and not x2. So only if both are negated, we get this whole thing here. So basically, if both are 0, if both are not true, right? So this is the important thing here. Like if this is 0, this is 0, then only we'll have this in high activation. You can see this. Like high activation means high value. And when does this get high value? When does this get high value? Now, not x1 and not x2 only gets high value if x1, right, and x2 are 0, because then they are not multiplied, and then the 10 gets into action, right? So this is basically, you can see, if you want to think of it, you can see that this only gets activated, meaning a positive value. This is sleeping until it gets activated when these two are 0. Otherwise, then this doesn't really have an influence, because then this would be 0, right? So 0 is the lowest thing they can get, because this is a sigmoid function. It has values between 0 and 1. And if anything else happens, then that they are 0, then this thing is always 0. All right? And here, it's just that this thing is 0 when either of them is 1, or when both of them are 0, and it's only non-zero and both of them are 1 when both of them are true. And last but not least, we have the OR function, right? So we have the OR function, our steady OR function that we discussed in the beginning, between these two. And now this one does not look at the input. This one only looks at these two, right? And I think this is a beautiful example to show you how a neural network works, right? So this doesn't care about x1 and x2. It cares about the output of this. So we can get complexity by having our departments, by connecting them. So, and then it's just the OR. So this is actually 1 if one of both is 1. So it's only the case here and the case here. And we have our XOR. And this is our XOR. And we've done it now. Okay. So last but not least, what I want to do before we next lecture we go to actual C, is something that I actually discussed with you already in AIBDS1. I just want to show you because we always have these binary outputs usually, right? So until now, all you saw from me is blah, 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 input layer, input layer, input layer, and then one output layer, right? So all my examples until now, maybe on the Blackboard, I think I used is one output layer. Now, this we can only do for binary classification, because in binary classification, automatically, if you if this is like a high value, we know that the opposite has a low value, right? Because it's either the one or the other. Now let's choose this example right here. What if I want to detect multiple things like pedestrian, car, motorcycle, and truck? Yeah, it's easy. Then I just use more neurons. And that's the beauty of ANNs. And that's basically it. So our output now is not one value, but our output basically is more than, is a vector now, right? So, and it doesn't have to look like this. Now, this is the thing that we want, right? What we want. We want to have a clear picture, but we could also have something like this, right? So, and now you're asking, do they need to add up to one? No, they don't. They don't need to add up to one because each function here can take values between 0 and 1. So they have to be each of 0 and 1, but they actually do not to sum up to 1. And now you think, that's a bummer. Yeah, and what we do then is actually we apply what is called a softmax function to these outputs. So these are unnormalized outputs and just normalize them, right? Softmax just means we take this for example, the softmax transformation means we have 0.05 divided by the sum of them all, by the sum, right? So basically it's 0.05 divided by 0.5 plus 0.28 plus 0.5 plus 0.75. So we have basically the portion of this, and then we get a value between 0 and 1 that adds up to 1, right? And this is called softmax. So if you read softmax, it just means that we have outputs that sum to 1, so we can identify the value at once. Yeah, it's not necessary. We can also pick the largest value if we just want to see what it is. And if it's clear, we just pick the largest value. And this is 0.75 in my example. All right. So next time, how do we get our weights, right? How do we get our weights? And the answer is we use gradient descent. We use gradient descent. This is how we get our weights. However, right? What do we need for gradient descent, right? So how do we train the network? So here we've done it by hand. This is not a possibility. How do we get the 10? How do we get the minus 20, right? Well, we use machine learning as we've learned it in AIBDS1, and we use gradient descent, right? But remember what we need for gradient descent, right? For gradient descent, we need two things. We need the cost function. This is the first thing we need. And then we need the derivative of the cost function, right? This is the second thing we need. So now, if until now, our cost function was fairly simple, right? And actually, this cost function doesn't look too hard either, right? You can ignore the regularization term for a moment. Now we can also ignore this whole thing, but what I'm trying to say is the cost function is not as simple now, right? Because we have all these stages here, right? So my problem is we now don't have one derivative, but we have multiple partial derivatives, right? And the matrix of partial derivatives is called a gradient. So these are all, because we have multiple parameters, partial derivatives, right? And we need all of them, right? Because this gradient effectively tells us who to blame. This tells us who fucked up, right? Who of these workers has what influence on the output. And so we have to go back. So we have the error here, and we have to go back, and then we have to blame. Who's to blame for the error? And we attach, so to say, we attach blame to each of the neurons, and the higher the blame, the more they need fixing, and the more the change in the gradient descent, right? But this we will talk about next week. Before we go, I have uploaded a document that is called E3, right? This is that document, right? E3 explains what backpropagation is. And this is the way how we get the gradient in neural networks. So basically, how we get the second thing we need. Second thing we need to train the model. We have the cost function, but we need also the gradient. So the derivative of the cost function, right? And in neural networks, this is not that hard. Otherwise, I could have just said, hey, guys, do gradient descent, and that's it. But it's not that easy in neural networks. So what I want you to do is I want you to look at this, right? There is a video here you can watch. Now, this is a great source. Like, full credit to that source. I love it. It's a great source. I could have explained it better. And we will use this, and I will go through this next time. And then we will understand how it actually, we will use the MNIST, the famous example. I always try to incorporate more examples. And then we will learn how we actually calculate the gradient. And we will finish up neural networks next time and to see, okay, what is the whole training process? What in practice do I need to take care of? And so on. All right. Okay, so watch the video. It will greatly improve your chances of understanding anything I say next time. Thank you so much. I will upload this as soon as it has compressed. Thank you so much. Remember, next week is holiday. I've also put this already in the e-learning. So there's a public holiday in Germany. So I will see you in 2 weeks in the lecture hall. Thank you so much for joining us. And yeah, see you soon.
Thank you very much.